Good morning, everyone, and welcome to today's webinar, Getting Started with LoRa using ARM Embed and the Things Network. You will have the opportunity to submit questions to today's presenters by typing them into the questions pane of the control panel. You may send in your questions at any time. We will collect these and address as many as we can during the Q&A session at the end of today's presentation. I would now like to introduce Jan Jongbom, who is developer evangelist from ARM, and Johan Stocking, who is the CTO of the Things Industries. Please go ahead with your presentation.
All right, thanks a lot, Danielle. Yes, my name is Jan Jongbom. I am developer evangelist IoT here at ARM. I'm also an applications engineer at ARM, and I'm joined here together today with Johan Stocking, who's the CTO of Things Industry and the co-founder of the Things Network. Now, usually Johan and me are in the same city. We're both based in Amsterdam. But today we couldn't be further apart because I'm speaking to you live from South Korea and Johan is in South Africa. So that's almost 14,000 kilometers away, which is pretty great. But this is the power of the internet and the power of computers. So we can actually deliver this webinar live for you from here. So if we're looking at the Internet of Things landscape, at least how it was until a couple of years ago, if you're looking for a machine-to-machine communication platform that allows you to short range and low power consumption, you're pretty well served. You got NFC for very short range. If you want to go a bit further, you can do Bluetooth Low Energy. If you're looking at basically in the same space, you have Zigbee and Z-Wave, wireless mesh technologies. If you're looking for higher bandwidth on short range, you're also well covered by Wi-Fi. But there's a bit of a problem. For a lot of IoT devices, you want range. You want to be able to reach your end nodes over a couple of kilometers. And up until a very short time ago, the only opportunity you had there was the cellular technologies. And those are 2G, 3G, 4G, traditional M2M, what the telcos call that. So there's a big opportunity for space there in the right bottom corner. For a lot of Internet of Things devices, we want the range of cellular, we want the power consumption of Bluetooth. And this is where LoRaWAN fits in. LoRaWAN is a long-range technology that consumes very little power, making it very suitable for many IoT devices where very little data needs to go over the line, because with low power also comes low bandwidth. So for use cases like a trash can that just needs to monitor its how full it is, communicate that back, that's something where a lot of IoT devices want to have, where cellular is way overkill. So LoRa is not the only technology that tries to address this. There's many choices currently in the market, and these are called the LPWANs, the low power wide area networks. We have Sigfox, which pioneered the field a couple of years back. There's Weightless, and there's also the telcos realized that this was something that the market was asking for, and they're currently rolling out technologies like narrowband IoT and LTE Cat-M. Now all of these technologies claim kind of the same thing, and that is 10 years of battery life and 10 kilometers of range, which sounds absolutely awesome. I mean, my phone has the 10 kilometers of range, probably to a base station, maybe a little less, but it dies within a day. And my Bluetooth beacon has 10 years of battery life, but the range of it might be 10 meters and not 10 kilometers. So on first hand, this sounds like an amazing technology that is combining the best of both worlds and is a perfect fit for the Internet of Things. Now, when I first heard about this, I was a little bit skeptical because how the hell is this going to work? So to explain how LoRa works and how it achieves these amazing capabilities, we're going to first look at the LoRa physical layer and show you why LoRa works through, well, physics. So the phi in a network model is the actual physical layer. So it does the modulation of a message and the demodulation, and then actually sends it over the network, through the air. So a typical radio signal is very basic. This is how every radio signal works. So we have a transmitter and a receiver, and if we want to send something from the transmitter to the receiver, we first put power in the message, the transmit power. You can express that in decibels or in milliwatts. So for LoRa, the transmit power that we use is 14 decibels or 25 milliwatts. It's actually not that little. It's pretty standard. It's the maximum that is allowed in the European ISM bands. Then there's a little bit of loss because your connectors are not 100% perfect and your cables are not 100% perfect. Then there's a little bit of gain. If like an antenna is, at least for LoRa, is very omnidirectional, but very often you don't want to send the same amount of power in every direction. The chance that your device or your gateway is in a horizontal plane is a lot larger than that it's right above you or right below you. So you can, with the shape of the antenna, you can put a little bit more gain into the horizontal plane, so we win a little bit there. Then the signal will go through the air. There's of course fading of the signal, and then there's path loss because you encounter buildings or you bounce off things, or you have to go through a wall. And then on the other side, the same principle happens again. Now, what makes it if a signal is received by the receiver depends on the receiver sensitivity. If the signal is stronger than the receiver sensitivity, that means that the receiver can decode the message out of the noise. This is a number that is dependent on the modulation scheme that you use. It's dependent on the speed of transmission, and it depends on the frequency that you use. This is where a bit of the magic of LoRa is. LoRa's modulation scheme is really good, and because how LoRa modulation works through a chirp spread spectrum, LoRa is actually able to detect signals under the noise floor. So where you normally wouldn't get any signal anymore, LoRa can still decode that. That's why the receiver sensitivity of LoRa is very good. So typical LoRa receiver sensitivity is minus 137 dBm. And if you combine that with the transmit power, 14 dBm, which is the maximum we can do in Europe, that gives you a link budget. And the link budget is how much signal you can lose between the transmitter and the receiver while the message will still make it across. And LoRa has a 151 dBm link budget. Now you might not have any idea what that means, but that is actually what gives LoRa the amazing range that it has. If you combine the link budget for LoRa versus other technologies, for example Wi-Fi, so this is the ESP8266 Wi-Fi chip, which is a link budget of 95 dBm, or sub-gigahertz 6 low pan, which has a link budget of about 120 dBm, and then you see LoRa, which is 150 dBm. You might think, well, so there's a 30 dBm between LoRa and sub-gigahertz 6 low pan, or 60 dBm between LoRa and Wi-Fi. What's the fuzz about? Well, decibels are a logarithmic scale. So it's not that LoRa has twice as good as a signal as Wi-Fi has, or a link budget as Wi-Fi has. It's actually not even 10 times as much. It's 2 to the 10th, because for every 6 decibel, you double your distance. So LoRa can go 2 to the 10 times as far as Wi-Fi, theoretical. And also a lot further than sub-gigahertz 6 low pan. That's just because the LoRa modulation is a lot better at getting the signal out of the noise than these other technologies are. So for theoretical range, this is what we can show, is that theoretical range of Wi-Fi, this is in absolute the best scenario, where there's no earth to speak of, no buildings, no nothing, is 550 meters. That is with the 95 dBm link budget that the ESP8266 gives you. LoRa, on the other hand, on 915 megahertz, gets to a theoretical maximum 850 kilometers. And that's crazy if you think about it, because the Wi-Fi chip we saw in the previous slide is actually sending with more power. So LoRa is using less power to get over 1,000 times the distance that Wi-Fi can do, theoretically. And this is absolutely amazing. This is yeah, the first time I saw this, I was very happy about this. I've been working with the technology for 3 years, and this never stops to amaze me. Of course, this is theoretical maximum. So Johan's company, the Things Network, they decided to do some tests, and they let go a weather balloon filled with helium and let it go up in the air. And they measured from base stations that were on the ground to see how far they could go. Doing it with a weather balloon is really nice because it goes really high, so there's no earth that can block any of your signals, there's no buildings. And through that way, they managed to get a distance on a normal certified European LoRa module, just sending with the maximum transmit power allowed in Europe of over 700 kilometers. That's truly amazing. It's a small, tiny end node and a large gateway on top of a building. Now, unfortunately, we don't live in free space, so in a real scenario, we're never going to see the 700 kilometer range. There's attenuation, so there's stuff in the way that your signal needs to get through. A brick wall can block 6 to 20 dBm of your signal, so that actually that halves the distance that you can go already per wall. There's reflection and diffraction, so that gives multipath signal from your device to the gateway or the other side. This might actually be good if there's only one way of reaching your device, and that's through reflection. You can actually reach the device without line of sight. However, if you have one direct signal and one reflected signal, the phases of those are inverted, and you can actually fade out the signal, even though the signal should have been really good. And then the last thing is that there's the Fresnel zone. If a signal goes from point A to point B, there is not just a direct line, there's actually a cloud of signal going from A to B, so you can draw an ellipsis around it. If a large part of that ellipsis is blocked, then your signal strength will go down very quickly. And unfortunately, the Earth is a really big mass. So if you have a receiver and a transmitter both close to the ground, then the Earth will be in the Fresnel zone, and that will have a deteriorating effect on the quality of your link. So the best thing there is to always put your receiver and your transmitter on a really high location. But unfortunately, if you have a smart trash can that is 100 meters high, not a lot of people are going to throw anything in it. So it has a deteriorating effect on network quality. So to get a better understanding of like a realistic link in LoRa, there's the Hata model. It's based on a 3D model of Tokyo. It's a model for calculating realistic path loss. So you can fill in your transmit height, your receiver height, whether you're in a large city, a suburb, or an open field, and that gives you the amount of link loss. And we can calculate that against the 150 dBm that LoRa gives you. In a large city with a transmitter at 10 centimeters and a receiver at 40 meters, we see a range of about 4 kilometers. But that is at the lowest data rate that LoRa gives you. So that's at 30 bytes a second. If you are going to send faster, so in this case 200 bytes a second, then your receiver sensitivity goes down. So we're going to see about a range of 2.5 kilometers. This is very similar to what we've seen when I was doing range testing in my previous job in Oslo. If you go to a suburb, then there's less attenuation, there's less buildings in the way, so you see about 9 kilometers at the lowest data rates. And if you put your transmitter and your receiver higher, then your range basically goes up with over 50%. So these are a bit more realistic. 4 kilometers in a city, 10 kilometers in a suburb. That's definitely doable on LoRa. If you want to learn a bit more about like how the modulation scheme works in LoRa, how the chirps work, and how LoRa can decode signals way under the noise floor, there's this really good YouTube video. We'll link to it at the end of the presentation as well. That does an excellent explanation of the modulation scheme in about 3 minutes. So that's how the LoRa physical layer works, and that's how LoRa gets its amazing range capabilities. And now Johan is going to talk about LoRaWAN, which is the MAC layer.
Yes. So LoRaWAN is LoRa and LoRaWAN are in the beginning. I think when you're new to the topic, it can be a bit confusing. LoRaWAN really is the bidirectional messaging protocol on top of LoRa modulation, and you can use other messaging protocols on top of LoRa. We also see that in the industry that companies are using the LoRa modulation and they add their own protocol on top of it. But LoRaWAN is a standardized protocol that is standardized by the LoRa Alliance and has wide support for devices, gateways, and network servers. So when we look at LoRaWAN and when we compare the protocol to other protocols that are familiar to us, for example, we can look at the Osi model that is being used to model protocols typically on the Internet protocol. We can see that LoRa is really in the physical layer, so it's really in the bottom of the model. In the data link layer we have channel management, data rate management, and MAC commands. And MAC commands are commands that are sent between the network server and the end device and that are not visible to the application, and these can, for example, be used to control the data rate of devices. So this is built in LoRaWAN. Also, there's addressing, there is gateway selection for downlink. So if you have multiple gateways that cover a single device, you can have a selection of gateways by the network, which is the best gateway to send a message, for example. In the transport layer, we have the tracking of the frame counters for uplink and downlink to perform the message integrity. to see if messages have been retransmitted or to detect a replay attack. So that's part of the transport layer. On the session layer, we have the over-the-air activation, which is a mechanism to create new sessions. And a session is basically a security context with session keys and frame counters and address, as I will explain a bit later. And finally, on the application layer, even which is also affected by LoRaWAN partially, because there is encryption of application payload. So there are basically two session keys. One is for the network and one is for the application. And LoRaWAN does not prescribe a binary payload format to use. So you can use any encoding on top of LoRaWAN for your application. There are three device classes in LoRaWAN. First, we have Class A. Class A devices are typically in deep sleep, and they send messages on intervals or events. So these are the typical sensors. So they are in deep sleep all the time, and then when something happens or on an interval, they send a message. And in order to send a message back to the device, so-called downlink, the network has to wait before the device sends a message, because after a device transmitted the message, there is a receive window. So the device typically stays awake for 1 and 2 seconds to receive a downlink message from the network. And then the device goes back in deep sleep. Class B is when the network and the end device synchronize a slot for downlink messages. So the gateways, they send beacons on an interval, and end devices listen to these beacons, and they basically that way sync with the network, and they wake up every so often to receive a downlink message. And this is configurable. It could be every few minutes or a few times per minute. And in the meantime, these end devices are in deep sleep. So this consumes a bit more power than Class A, but it's really good to get downlink messages to end devices. And Class C finally is where the network initiates communication. And in this model, the end devices are continuously listening, and the network has the opportunity to send downlink messages at any time. And of course, this requires quite some power on the end device, and so we typically see that end devices have a power supply, or that this mode is being used temporarily, for example, for firmware updates. Class A, all the LoRaWAN end devices are Class A, but they can switch to Class B and Class C and back to Class A depending on the application. So the typical network topology is as follows. So we have end devices, we have gateways, there's a network server, there's an application server, and there is the user application. And with LoRaWAN, which is different from, for example, Wi-Fi and Bluetooth and even cellular, there is no pairing between a device and a gateway. So there's actually no connection between the two. The gateways do not know the end devices. They just receive data on the frequencies that they are listening on, and they forward the data packets to the network server that the gateways are connected to, and the other way around. So the transmission, the network server selects the gateway for downlink transmission. And this works really well, because in order to add capacity to a LoRaWAN network, the only thing you need to do is place another gateway, and there's no need to configure anything on the end device. On the security level, as I mentioned before, there are two session keys. So we have the network session key that's shared between the end device and the network server, and we have the application session key shared between the end device and the application server. And the application session key is really used for encryption and decryption of application payloads. LoRaWAN uses the so-called ISM bands, the industrial, scientific, and medical bands, which are unlicensed. So although the spectrum is regulated almost everywhere in the world, not the entire spectrum is licensed. So you can set up your own Wi-Fi network, you can set up your own personal area network on Bluetooth, and likewise you can also set up your own LoRaWAN network. There are different frequencies being used though across the world, and this is basically a map of the frequency plans that are now specified by the LoRa Alliance Technical Committee. This is part of a document that's called the LoRaWAN Regional Parameters. And if you, for example, you see the blue shades, that's and devices that operate around 915 megahertz. The green shades are around 868 megahertz, and red, China, is typically between 470 and 510 megahertz. And so these are also three different types of hardware, different radios that are optimized for these frequencies. And of course, you can also use LoRaWAN in other regions that are not colored here. For example, here in South Africa, the European frequency plan is being used because South Africa is a member of the ETSI. So ETSI countries follow the European plan, and FCC derived derivatives are following US 915 plan. So you can basically use LoRaWAN across the world with typically 3 different radios, and currently more regional parameters for other regions are being specified by the technical committee. So since you can set up your own network with LoRaWAN, we decided 2 years ago to start the Things Network, which is an open network, and our mission is really to build a decentralized, open, and crowdsourced Internet of Things data network that's owned and operated by its users. So what this means is that we build the network technology, we build the network server is open source, and people can create the network themselves. They can set up gateways, they can connect it to the network, and this creates one big open network. And this started in 2015 really as a community project. To demonstrate this, and also to demonstrate the need for such a network, we had a very simple use case. And we are based in Amsterdam, and in Amsterdam is full of boats like these, and they typically run water. So we decided to create a boat sensor, which you can put in the boat, and if it detects water, it sends a message to the network. And this is actually a pretty good use case for LoRaWAN, because you cannot use Wi-Fi because you don't know the passwords of the Wi-Fi access points around you. You can't use Bluetooth because the range is so short that you might as well just look in the boat. And LoRa is actually really useful for this, because the only thing the boat needs to do is send a message. You don't even need to send payload. And so this was 2 years ago, and since 2 years, we achieved a lot of things with the Things Network together with the community. So we are now active in more than 90 countries. We have more than 540 communities on our network, which are local groups that organize meetups that are run by a community initiator. You can look on the map to see if there's a community around you. Like Jan introduced, we have we reached more than 700 kilometers of range in free space. We have more than 1,600 gateways connected, which makes it the biggest global network, LoRaWAN network. And finally, we have more than 27,000 users. And this is really the size of the community. But we often get the question: so who are these? What is the community? So we have startups, corporates, governments, educational institutes, students, independent enthusiasts, but also building operators that just have a tall building and space to place a gateway. So it's basically anything. It's really a LoRaWAN developer community. And our mission is really also to drive the developer community by guiding them through the process of creating a prototype, building your first batch, and then go into mass production. And where ARM Mbed and LoRa really fit in is this, also already on a very low scale, but because it's so cost effective. So even if your first batch is a few hundred units, LoRa is very useful, it's very cheap. ARM Mbed is a very good and easy to learn operating system. And there are plenty of developer kits around, as I will show you later in this presentation. And also when you go for mass production, LoRa is very suitable. You can build your own radio, your own LoRaWAN module, still use ARM Mbed and be just aware of memory consumption and computing power. So the size of the number of IoT devices that is expected in a few years is going to be in the tens of billions. And what we really see is that most developers, they really have a web background. So they are very familiar to cloud services, to JavaScript, to Rust, to Go. And this really large-scale deployments and the requirements, the things that you need to know for large-scale device manufacturing is quite a different area. And we really try to bridge this, to make it easy both for embedded developers to connect to cloud platforms, but also for developers that are used to cloud and to JavaScript to start building their first embedded solution. So that's really what our role is. And we really do this together. So we always say, you are the network, you can place a gateway, you can contribute source code on GitHub, you can start a community or join a community, or you can share a story on Things Network Labs. Finally, we are organizing a conference where both Jan and I are speaking. It's the Things Conference. It's 1 to 3 February next year. And we have a 10% discount code for all of you watching this webinar, which is I know a speaker. So note the code and sign up for the Things Conference. Jan will take it a bit further from here to dive deeper into Mbed OS and see what that offers.
Yeah, so I hope that you guys are all very enthusiastic right now with LoRa. We went over the physical layer, went over the Mac layer, and Jan did an introduction of the Things Network. Now, what if you want to get started doing this right now? ARM Mbed is ARM's platform operating system, ARM Mbed OS, which we target IoT end node devices. If you're aware with Mbed, but you haven't paid attention for the last couple of years, Mbed used to be a way of making it easy to do Cortex-M development up till a couple of years ago. We've invested heavily on it. We currently have 400 people working on Mbed on the various parts of it, and it's currently really a abstraction layer for Cortex-M devices. It comes with an RTOS based on Kyle RTX, but it also comes with a set of IoT connectivity methods, a lot of portable drivers with integrated security, integration with the new trust zone in V8M. It's a really great platform operating system to get your device in the hands of customers a lot faster. What makes this nice for LoRa is that because we have portable drivers currently ported to over 150 development boards, it doesn't really matter which MCU you want to use, whether it's a small Cortex-M0 or a beefy Cortex-M7 with 2 megs of RAM. We have Mbed already ported to that. What's nice then on the LoRa side is that we have, on top of those portable drivers, we have connectivity libraries for example, BLE, cellular, Wi-Fi, but we also have a LoRaWAN stack. So you can take that, take our stack, take our hardware abstraction layer, and run that on almost every Cortex-M device out there. And that makes it really easy to port a LoRaWAN stack onto your device if you're a module maker and you don't want to deal with that, or if you're a device maker and you want to get to market faster, because we've done all the heavy lifting for you already. Mbed is one of the things that people see when they read about Mbed is the online compiler. That's something that started the project. Back in 2009, we wanted to make Cortex-M development a lot easier to set. So we created an online compiler, which was quite a shock to a lot of embedded developers, because it used to be, up until a couple of years ago, that you needed a Windows machine, you needed to buy your tools, you needed to buy your IDEs to actually start doing something for embedded devices. So we changed that. The online compiler is used a lot. I think we do 1.5 million compiles a month at the moment. But we've evolved since then. So we have, in our core tools, we have Mbed CLI, which is our offline development tool, but we also have a variety of IDEs, commercial ones. So we have Kyle, ARMC5 and ARMC6. We also support for IR. And if you don't want to pay for your compiler with GCC support. So we integrate with a lot. So Mbed is no longer the online compiler. It's a very wide platform operating system supported by many boards and many radios. So if you want to get started with Mbed and LoRa, there's two approaches that you can take. You can either go the module way or the raw radio way. So for the radios, there's currently two radios that you can buy. It's the SX1272 or the SX1276. Those are the only radios available. If you buy a module from someone, that radio is going to be in there. This is also one of the potential largest downsides of LoRa, is that there's only one manufacturer currently making the radio, and that's Semtech. So if you go to the raw radio side, that means it's going to be cheaper because you can do all your own R&D. The design cost is going to be higher because you need to do your own RF design and you need to do your own certification. If you don't want to do that because you don't have an RF engineer or you're doing a smaller batch, then going a module way could be better. You pay a little premium on it, but very often these are already certified. They already shielded. The RF design that is done is good, and it makes it a lot easier to integrate in your own design because you stick the module on your PCB, and very often just a simple two-layer PCB is enough. So if you, depending on what you want to do, we have support for both actually in Mbed. So we have full support for the 1272 and 1276 radio, and we have also a variety of modules that we support within Mbed. After you pick the device or multiple devices, you need to start picking a gateway. There's also a wide variety of those on the market. As Johan said, a gateway is transparent within the LoRaWAN context. So the gateway, the only thing it does is get signal out of the air and then forward it to a network server. So what gateway you want mostly depends on where you want to place it. So the Curlink IoT station is one that's used by a lot of telcos. And that's nice because it's IP67, and has GPS on board and cellular backhaul, waterproof. The Multitech conduit is one that we use a lot within ARM because it's a nice small one that is the size of a Wi-Fi router you can place indoors. Now the interesting part here is that all of these gateways are essentially the same on the radio perspective. I mean, they differ a bit in the RF on the RF front end, but they're all based around the SX1301 and the SX1257 chips. So internally, the same radio chips are used everywhere. So if you're looking for a very cheap way of building it, actually the cheapest way right now, you can just buy a concentrator board that has those chips on it. It's the IMST IC880A, which can be bought for about 200 euros. Hack up a Raspberry Pi to it and get started from that. So 200 euros is about the lowest cost you can go. If you want to go a bit higher, telco grade stuff, Curlink IoT station costs about 2,000 euros. That's about the range right now. We have prepared a demonstration. We're going to show that through videos instead of through a live feed because the webcam apparently doesn't properly work with the webinar software. But we have the LTEC FF1705. It's a development board based around the Multitech X-Dot. It's a board that we specifically built for a conference a couple months back. So you see the Things Network and the ARM Mbed logo on it. We'll use the Multitech conduit. It's a gateway from Multitech. And then data is being sent to the network server, hosted by the Things Network, and then we'll do some visualization through Kaya and my devices. And I'm going to hand it over to Johan, who's going to lead you through this demo.
Yes. So we have on the hardware side, indeed, this what we are having showing for this quick demonstration. So we have the end device featuring a Multitech X-Dot and an ultrasonic range. And the simple use case is that it sends the measured range over LoRa and that you can visualize that in KM. So it's a very simple use case, very easy to build. So we can, for example, detect moving an item. So the first thing to do as a developer is to create an application in Things Network. And in the Things Network console, you can manage applications, gateways. So you can go to the applications pane. And here you can register a new application. And applications in the Things Network have a unique application ID, which you can make it yourself. You can use this in URLs. It's just very easy for you to remember. You can give it a description. There's an app EUI, which is a LoRaWAN identifier for your application. And you can get one from us, from our blog, but you can also use one yourself. You can register your application, for example, in this case, to the European router. So this is a brand new application in the Things network. The next step is to register a device, and LoRaWAN radio modules, they already have a def EUI. So for example, the Multitech XDOT has a def EUI printed on it. It's very, very small, but it's there. If you have your own transceiver, then you need to get a def EUI from a IEEE block, which you can purchase there, and really the combination of EPUI and def EUI must be unique. So what I'm just going to do is enter this def EUI in the console. So when registering a new device, we can just go to the devices pane, register device, enter an ID. So this is again just a name for you to remember easily. Enter the def EUI that is on the module, and then register the device. The Things network creates an app key for you. You can also enter one yourself. This is really the security key that is registered in the application server, and of course you can also run these components yourself to actually keep the keys local in your trust of control domain. And so this is the app key that we generated. And then the next step really is to put the pieces together and to start coding. And this is the online compiler that Jan just introduced. It's very convenient. You don't need to install any tools. And I prepared a very quick demonstration for this webinar, which requires just very simple configuration. And here in the code, you can see that you need to enter an EPUI and the app key. So these are the two identifiers. And together with the def EUI, that's basically the three things that you need to join the network. So you can copy the EPUI from the console, copy paste it to the code in the online compiler, and the same for the app key. And what happens in large-scale production is that this is done in a part of the production process in a trust zone in the factory, for example, and there's a join server, but that just for getting started, we just hard code these values in the end device. So that's really the configuration. Then we here have a very simple application that measures the distance. There's a callback when the distance that has been measured by the ultrasonic changes. There is some configuration of the XDOT. So we have the app EUI that we're setting the app key. We are enabling public network because the Things network is a public network. We disable acknowledgements. So it's just very simple configuration. And then that's all we need to join the network. And this is a library that's built by Multitech that makes it very easy to use LoRa in embed. Here's the main loop. It's a very simple application. So after joining, we start measuring with the ultrasonic if there is anything to send. So when the measured value changes more than, in this case, 2 centimeters, we actually send it to the network. This is to reduce the amount of data that we send because it's quite limited with LoRa. We use Cayenne LPP payload, so we add it as an analog input, the measured distance in centimeters, and then we basically just send it to the network. So that's basically all you need to do to build a very simple application. And then here in the online compiler, there is a compile button, and this basically compiles the application for you and then gives the compiled binary file as a download. So it's just a file that you get from the online compiler, and you can drag and drop this to your device, which mounts in Mac or in Windows or in Linux as a USB stick. So you basically just drag and drop the file to, in this case, the end device, and this also flashes the end device with the firmware. So that is just the coding on the end device. And then when we go back to the Things Network console, this is, for example, the gateway that we're using. It's a Multitech gateway. that we have here temporarily in table view, and we can go to the traffic and really see what is the raw traffic that it is receiving. So this is traffic, other traffic, TTN traffic here in Cape Town, and this is the serial connection with the demonstration device. And here we see that it's now joining the network, and while this device is joining the network, we also see in the gateway traffic a so-called join request from the app UI and the dev UI. That's your device. And you also see the first message, which is the first row, frame counter 0, which is the first data packet that it sent. So this way it's actually really easy to see and get very good insight in the gateway traffic. And then finally, we want to do something with the data. So for example, when an item is moved, the measured range changes, and we want to visualize this. So when this happens, in the application data, you can see messages coming in from the end device. So here we actually see the messages that the end device is sending. So we see the binary payload, and we also see the decoded payload. So the analog in is the number of centimeters that the ultrasonic measured. And we know this because we set the payload format to Cayenne LPP. That's also what we're using, and we also enabled the Cayenne integration. That's one of the many integrations that we have, but Cayenne is a very easy and very convenient tool to visualize data. So this is Cayenne. You can log in, you can go to LoRa, you can select the Things network, you can select the device that you're using. So we have a custom device, and we're using Cayenne LPP as a payload format. So just select Cayenne LPP. We need to enter the dev UI to identify the device. It's just very simple steps, and that's it. And the next time an end device starts sending data, we see the data here coming in and have it in a very accessible way, visible. You can create histograms here as well. So this is very, very simple hands-on getting started with ARM Embed, the Things network, and visualization in my devices. Cayenne.
All right. So so we did a demonstration of how to connect your device to the Things network, all nice and brief. So there's a couple of more points that I want to touch on. So the comparison against other LPWANs. LoRa does not exist in a vacuum. Other low-power wide area networks claim the same thing. They claim 10 years battery life, cheap module costs, etc. So where does LoRa stand against these other LPWANs? Sigfox, if you talk about low-power wide area network, Sigfox was basically the first one, launched a few years back. Basically started the whole idea of running in an unlicensed spectrum and sub-gigahertz and having a high link budget. Sigfox is very similar in link budget to LoRaWAN if you send data from a device to a gateway, so you can expect the same range and very similar data rates. A downside that Sigfox has is that if you want to send data from the gateway back to the device, it was never really meant to do that. And Sigfox modulation is a bit harder to demodulate than LoRa's modulation. So from the gateway to the device, they cannot use the Sigfox modulation, and it gives you a lower link budget. So it's a lot easier to send the data from the device to the network than the other way around. Another potential downside that we see is that everything is controlled by a single company. It's kind of the case with LoRa because you need to buy the chips from Semtech, and it's the only company where you can buy the radios from at the moment. Sigfox, however, wants to control the complete network side. So where in LoRa you can just buy the radio and then whip up your own LoRa network, Sigfox, the company, wants money at every step. If that's good or bad, I mean, the nice thing there is that they built the network for you, so you don't need to do that yourself. You just pay for connectivity, but it gives a bit less freedom. What is nice by Sigfox is because the radios can be made by multiple vendors, that gives cheaper radio cost. So a LoRa radio, a raw radio, right now in low volumes is about $6, and a Sigfox radio can be bought for about $2. So that's an immediate advantage. However, you're gonna leak some money with operating the network. Then, of course, the telcos realized that low power wide area networks were actually a thing, and they started doing some stuff in the 3GPP. There's two technologies that the 3GPP has come out with. One is LTE Cat M1, and the other one is narrowband IoT. The biggest difference here, at first, is of course that the telcos use licensed spectrum, and licensed spectrum is relatively expensive. United States in the 2008 wireless spectrum auction, they sold off the 700 megahertz band. It's pretty good for IoT purposes. And in total, they charged $19 billion for that. And that money needs to be recouped at some point. For LTE Cat M, one of the downsides is that the RF design is relatively complex. I mean, it's a LTE front end that you need to integrate, so potentially that's going to lead to higher module costs if you compare it to LoRa, Sigfox, and narrowband IoT. The nice thing there is that LTE is a very mature technology. It has very high bandwidth, and thus it also has stuff like native IP. So that's all stuff that's really nice. We're going to see LTE Cat M. We actually see some deployments already happening. So this is going to come to market very fast, faster than narrowband IoT. There's some similarity in power management. LTE Cat M has the power save mode, which is very similar to LoRaWAN Class A, and they have HEDRX mode, which is very similar to LoRaWAN Class B. So everyone borrows a little bit from each other. They also use 1.4 megahertz channels, so those channels are a lot wider than narrowband IoT, which uses 200 kilohertz channels, which is a lot closer to Sigfox and LoRaWAN. Because narrowband IoT is not bound to the ISM band, they can send a lot louder. So LoRaWAN and Sigfox are bound to 14 dBm, 25 milliwatts to send. That's something that narrowband IoT doesn't have. So narrowband IoT can send with 23 dBm or 200 milliwatts. That makes it a lot easier to reach your devices or your end nodes, and also means you can send faster. So narrowband IoT both has higher data rates and a higher link budget, which is really nice if you want to send some more data over. And it's also a way of saving power because your device can go back to sleep a lot faster. We like narrowband IoT quite a lot in ARM as well. We have some IP there. We're going to be integrating this in Mbed very soon as well. I think it's a really great technology because it's a relatively simple RF front end. I'm expecting to see modules that are going to be more or less as cheap as LoRa. There is still a bit of risk because it's a very new technology that there's like IPR, intellectual property risk. We kind of understand that with LTE Cat M. I mean, it's LTE. It's been on the market for quite a while. We know who the IP holders are. It could be that someone jumps out of the bushes when NB-IoT gets a lot more popular. There's a bit of a problem with sending data from the gateway to the device. There's a lot more capacity from the device to gateway, so sending large payloads like firmware updates could potentially be an issue. But for a lot of IoT devices, that's not going to be it. It's going to take a little while before narrowband IoT is reaching maturity. Still, some people are not sure what it actually means. Is it going to do IP? Well, it depends who you ask. The packet size is pretty small, so you need to do fragmentation if you want to do stuff like TLS. So we already saw that when we were trying to port our own TLS library. But overall, when they hit it, then I think narrowband IoT is really cool. It just depends. Do you want to pay an operator, or do you want to be able to build your own network or not? It's a bit of like a last, like a one more thing thingy. A lot of people, when they talk about LoRaWAN, they say, well, LoRa is not suitable for production deployments because it doesn't do firmware updates. Johan and me saw that as well. So for the last year, we've been working together with the LoRa Alliance Technical Committee on getting a number of new specifications approved. We'll hope to do that. Hope to get final approval in Q1, but we have the drafts out right now, which actually enable multicast firmware updates over LoRaWAN in a relatively efficient manner and actually fast manner, actually adhering to all the duty cycle limitations that we have in Europe and in the United States. If you want to learn more about that, go to bit.ly LoRa update demo. So that brings us to the end of this webinar, and we can switch to questions. Here's a recap. First of all, LoRa is absolutely awesome. I have been working with the technology for the last 3 years. The range that it gets is phenomenal. It's absolutely phenomenal. if you use your device in Class A mode, the battery, your power consumption is also absolutely phenomenal. If you have a water meter that only needs to wake up once a day, you can easily go for 10 years on a 500 milliamp hour battery. It's pretty cool. Because it's all in because all in the ISM band, open spectrum, getting started is also really easy. Just get a development board and get a gateway. That's it. If you start doing that, go with MBedOS. It's an actual proven platform operating system. We're expecting to ship over 8 million MBedOS devices next year. We have excellent LoRaWAN support. We're coming with a new LoRaWAN stack, and we're tracking LoRaWAN 1.1 specification, and we're adding that support to our stack as well. If you want to get a network, look at the Things Network. It's the absolute developer community for LoRaWAN. The Things Network forums is where everything across LoRaWAN is discussed. The Things Conference is where everyone's coming together. And the Things Network is currently the largest LoRaWAN network based on the number of gateways out there. And last, if you want to learn more, come to the Things Conference from 1 to the 3rd of February, because Johan and me are both speaking there. And if you show up there, I'll buy you a cookie. With that, thank you, and we can switch back to Danielle for the questions.
Awesome. Thanks, Jan. We actually had one question about where the conference is located. Where's the location for the conference this year?
Yeah, the conference is in Amsterdam. It's a very good question. So it's at our office of the Things Network in Amsterdam, which has direct flights to almost everywhere, and it's a really nice city to visit. And
exactly.
If you're lucky, Jan and I give you a private tour in Amsterdam.
You don't even know the excuse to go visit Amsterdam. It's a beautiful city. All right, so let's just launch into questions. We've not really got very much time, so I'm going to very quickly have a look at the questions that came in over the course of the presentation. Thank you, guys, for your questions. Let's start off with the question about which type of class, device class, I suppose, is best for real-time application scenarios like vehicle tracking systems.
So I would... It really depends on the direction of where you're sending data. So if it's really from the end device to the network, then Class A works fine. The latency is really low from sending data to receiving it, but since LoRa is a radio protocol and it's used in the unlicensed spectrum, there is no guarantee that a message is received. But you can use confirmed uplink if you need to be really sure that the message has been received, so that at least the end device knows that it had not been received by the network. If you need real-time channel to the end device, you use Class C. I would honestly not use LoRa for self-driving cars because it's. I would say that the protocol is not really suitable for that kind of high bandwidth communication. But so it really depends on which direction you're sending.
Great, thank you. So, Jan, going back to the range power axis, where does BLE 5.0 fit within that power axis? Does it start taking some of the LoRa cases?
I see it more in the direction of the 802.15.4 mesh tech, like 6LoWPAN and ZigBee. We're going to see basically doubling of range of BLE devices, and then we're going to see meshing. I mean, right now Bluetooth does flood mesh, but when we see proper meshing implemented, it's going to go a bit further, but not in terms of like the LoRa ranges. Doing a bunch of hops over a few hundred meters, definitely possible. If you want to go further than that, then an LPWAN is going to be necessary.
Okay, great. So since vertical transmission into the sky is virtually obstruction interference free, is it possible to have a satellite gateway for LoRaWAN?
That's a good question. Theoretically, yes, you can get that far. The problem is that if you have a gateway, LoRaWAN gateway on a satellite, it will receive so much traffic from Earth. There will be so much noise that it's going to be impossible to actually demodulate a message out of that. So it's really a capacity issue. But if you just look at the modulation itself, then it will definitely work. There's actually going to be a presentation about LoRaWAN from space on our conference. And that will actually cover this particular topic. So let's keep an eye on that.
Great, thank you. Now, we had another question about collisions on Class A devices. So The question asker says, a transmit of approximately 32 bytes lasts 2 to 3 seconds. Can multiple devices send data on the same channel to the same gateway at the same time?
So LoRa is also pretty resilient against other messages happening, especially on other data rates. So as long as they're not sending it at exactly the same time. Your 32 bytes is a bit negative. I mean, like the fastest you can go is spread factor 7, which takes about 100 milliseconds for that payload, and then the slowest is about 1.5 seconds. As long as they don't so first, LoRa has multiple channels. So in Europe we have 8 channels, and the channel selection is random. So the chance that they're both on the same channel and at the same time is about 1 in 64. And then LoRa is still pretty resilient against other LoRa interference on it. So as long as there's a bit of randomized timing in there, you're not going to see that much collisions. Of course, if you have a lot of devices on spread factor 12 and you're all receiving them, then the chance of collisions goes up. But the idea of LoRa is that you enable adaptive data rating. So if a gateway can hear you loud and clear, then you switch to a faster data rate. So if you see this kind of problems, adding an extra gateway somewhere is a really easy way to mitigate this problem.
Awesome, thank you. Is LoRa suitable for firmware updates for small embedded devices? I think this speaks a bit to embed.
Yeah, so this is actually a really good question. I think in general, LoRaWAN is, the issue is indeed bandwidth. So there are actually different challenges that we see here at the same time when it comes to firmware update. You need, firmware updates is of course very downlink intensive, so you need to send quite a lot of data back to the end devices. So you want to update multiple devices at the same time. For that you need multicast. If one firmware update does not fit in one message, so you also need to fragment the firmware into very small packets, into fragments, and broadcast that over multicast. And also you need to account for packet loss, because multicast is one direction, so you need to have a way to do forward error correction. And these 3 mechanisms is something that we built and we have working in a demonstration setup. And currently the technical committee of the LoRa Alliance is very close to releasing the specifications of how this all works together. But Jan and I did a demonstration, and in the link here that you see on this slide, the third link brings you to an article and a video where we demonstrate firmware updates over LoRaWAN.
And we have a reference design of the firmware running on a Cortex-M3 with 32K RAM that implements this spec, and it also implements Delta updates over multicast. So that's actually there. It's licensed under the Apache 2 license. So when the spec comes out, and we have the first network servers that out there that support it, Mbed will be the first platform that actually supports this.
Awesome, thanks guys. We've got loads of questions coming in. I just want to mention that we'll take a couple more, but continue to enter your questions. We do plan on, or Jan plans on authoring a Q&A blog post on os.embed.com in the coming days, so keep them coming. So I had another question about app EUI, which is being redefined in the next release of the LoRaWAN specification. How should that be used, or I suppose tackled once it's redefined?
Yes, so in 1.1, LoRaWAN 1.1, this is indeed redefined to be the join EUI, and typically what we'll see is that the so-called join server will issue the join EUI for you. So depending on which party you trust with your LoRaWAN root keys, you get a join EUI, and this is a reference for the network server to contact the join server of choice. So the it's really a reference to the join server, and then it doesn't really matter which network server you're using, because your root keys will be in the join server. So it's actually a big security improvement in LoRaWAN.
Awesome, excellent, thank you very much. So we've unfortunately run out of time today. We will have a second session later on this afternoon for those located in Europe and North American time zones, so keep an eye out for that. Thank you very much to Jan and Johan for your time today. As I said before, if anyone has any other questions, just continue to enter them into the questions pane. You will also receive a follow-up email within 24 to 48 hours with a link to view a recording of today's webinar. So on behalf of ARM and all our presenters, thank you so much for joining us today. Have a great rest of your day. Thank you.